Hello, my name is Aubrey Campbell, and the topic of this presentation will be the importance and methods of dimensioning and tolerances on manufacturing assemblies and the various different methods to validate those tolerances. So before we start talking about different methods by which to evaluate tolerances and their stack-ups in assemblies, we should probably first understand why tolerances and dimensions are even important. First off, nearly every part that is machined is intended to go into an assembly. And as the number of parts in an assembly increases, that means the tolerances on each part plays a more and more critical role. And so if more parts come out of tolerance, then you're going to have your assemblies more and more failing and not performing or going together as expected. Now this has severe implications with respect to manufacturing time, especially cost. So understanding the importance of tolerances and dimensions and the fact that they are directly related to how well our assemblies go together overall, and the fact that we want all of our assemblies to go together and function properly and as expected every single time, we see the importance placed on tolerances and dimensions. But we need to know how to apply those tolerances and dimensions, and that's done through a framework called Geometric Dimensioning and Tolerancing, or GDT for short. Once we use GDT to apply geometric dimensions and tolerances, we evaluate those by way of different analysis methods called tolerance stack-ups. Given that GDT is just the framework for which dimensions and tolerances are assigned to parts, it's still important to understand that it exists and what its role is, due to the fact that it's not often taught in engineering schools anymore, and it's crucially essential to tolerance engineering, which is becoming more and more important in industry as the demand for increased precision and higher quality parts rises as technology increases. As such, you should at least be familiar with the basic symbols that are going to be used to define these tolerances that we're going to discuss and evaluate by way of different stack-up methods. And these here, as you can see, are the 14 symbols that are used by GD&T to describe different features and tolerances associated with them. These would be associated with different feature control frames on a part drawing. So once you understand GDT and how to apply dimensions and tolerance parts and those dimensions, then you can start to validate those tolerances and see that you're using the best tolerances possible for cost and effectiveness of machinability. And you will use tolerance stack-ups to do this. Now there are many different types of tolerance stack-up methods, and that's what this paper and presentation, the heart of it really is going to compare those different methods. Now this can be a difficult concept to grasp, but in general the purpose of stack-up analysis is to establish the dimensional relationships within a part or assembly. It enables part tolerance to be optimized while maintaining functionality and maximizing part interchangeability and allowing minimum manufacturing costs to be achieved. So as I said before, there are of course many methods for tolerance stack-up methods, but for the sake of brevity and how long I have for this report, we will look at two, and that will be worst case scenario and statistical tolerance analysis. The worst case analysis method is also known as a linear stack-up method, and it's the most common and most basic method for predicting the effect of individual tolerances on the whole assembly. In this method, tolerance analysis is done by assuming that all of the individual tolerances occur at their worst limits and dimensions simultaneously. And then that's expressed by the equation that you see on the screen there, where n is the number of constituent dimensions in the dimension chain, and then delta I is the tolerance associated with the dimension. Now this approach is most applicable when the volume of the production is going to be very small and 100% of the production run has to be accepted. One of the more powerful tools in the statistical tolerance analysis approach is going to be the Monte Carlo distribution. Now, the Monte Carlo distribution is one of the most powerful tools for tolerance analysis of mechanical assemblies because it is used for both nonlinear assembly functions and non-normal distributions. It is based on the use of random number generator to simulate the effects of manufacturing variations on assemblies. And the distributions that it's taken into account, you can see are illustrated in the image there on the screen. And the idea is that the distribution between good and bad will end up equaling out across the whole scheme. So, as I said before, there are many statistical stack-up analysis methods. Some others that are more common are the root-sum square, the estimated mean shift model, the Taguchi's method, reliability index method is another one. I don't have time to go over those because of the brevity of this report, but you should be aware of them, so you can look into it further on your own if you want to understand the statistical analysis of stack-ups. So what all of this comes down to in the end really is once you use GDT to apply your dimensions and tolerances, you're going to have to choose a method by which to analyze the validity of those tolerances that you've chosen. Now, how do you choose which method to use? There are so many out there. Well, it's going to be driven by 3 different product design philosophies, and that's the engineering-driven design philosophy, which basically is the most liberal for engineers because it's a best guess type situation and based on experience of the engineer. So there are obvious downfalls there. But that is one of the design philosophies that you'll use. Another one is the process-driven design. Now this one is based on the tolerances and of the machines that you're going to use to put the features into your parts. So the problem with this process is that you could end up having parts coming off that look like they are good, but they won't work in the assembly. And then the third one is the inspection-driven design. And the inspection-driven design takes into consideration the instruments that will be used to inspect the parts coming out. And so these are the 3 different philosophies that you'll use to decide which stack-up method is best for you.